right, so here's your wonderful spring break chemistry video. We're going to talk about acid-base stoichiometry and neutralization reactions. So this is 7.4. So first of all, we're going to look at how this type of concept can help us to determine the molarity of a solution if we don't know what that solution's concentration is. So we got to kind of define a couple of things first, and I want to take a look at this word right here, titrated. And when you hear that word titrated, that just means that we're going to run a specific process that is going to allow us to determine the molarity of a solution. Okay, titration is that process of doing that. And in essence, what we'll do is we will take a specific material. In this case, we're going to talk about, let's talk about potassium hydroxide. So that's a base. Okay, and to that, we are going to actually add an acid. So we're going to add in an acid. So let's just add in hydrochloric acid. Now, let's say that we know the molarity of the hydrochloric acid. Maybe it's 6 molar. By figuring out how much HCl needs to be added to the potassium hydroxide to cause neutralization to happen, we'll be able to find out the concentration of that potassium hydroxide. So in a nutshell, real briefly here, that's the concept of a titration, and we'll go over it more in depth when we get into section 7.5. The math behind that process, though, is an interesting concept, and that's what we need to talk about right now. So let's look at a specific case in which we do have an Erlenmeyer flask, and this flask is going to contain 140 milliliters of the potassium hydroxide, KOH. We have no idea at this point what the molarity of that KOH is. Now we're going to add an indicator into the potassium hydroxide. So purple dots here are going to be the indicator going in. Okay, and the solution is going to stay the original color that the potassium hydroxide was. We're then going to add in our acid. So now we're going to add in the hydrochloric. We do know the molarity of the hydrochloric acid. Let's say that it's 0.05 molar. And as we add that acid in, we see that at around 50 milliliters, a color change starts to occur. Well, that color change, if we use the appropriate indicator, is going to tell us something very, very important. Once the color change happens, or once the indicator starts to shift, at that point in time, we now know that the moles of the KOH are going to equal out the moles of the acid, in this case the HCl. Okay, that's a really super important point, and that's going to help us guide our math through this process. Okay, so the moles of the KOH are going to equal out the moles of the HCl. From there, if we get that premise, well, the math is nothing new. We've done the math already. So let's figure out how to work this. So again, we want to determine the molarity. So our end game unit is going to be capital M for molarity of potassium hydroxide. I suppose I should put that in blue because my base has been in blue. So capital M KOH. All right, so how do we get there? Well, let's go ahead and start out with the total volume of the HCl that we began with. It's going to be that number right there. I'm going to switch to a different color here. So we have 0.05 liters. I'm going to change that to liters right away, HCl. Because what I'm trying to do here, folks, is figure out how many moles it took for the change to occur. How many moles of acid it took for the change to occur. Well, to figure that out, I'm going to have to multiply the volume by the molarity. And if I do that, the liters will cancel out. Okay, so 0.05 times 0.05, if you do that quickly on a calculator, if you've got one handy, that's going to come out to a small number. That's going to equal 0.0025. That's going to be moles of HCl. Okay, moles of HCl. Now, if you were to look at the equation for this particular process, you've got hydrochloric acid plus potassium hydroxide. This is a neutralization reaction, so you know one of the products is water, the other is a salt. And there are 1s for the coefficients all the way throughout this reaction. So what this means is that if it required 0.0025 moles of HCl to reach that equivalence point or that equal point, then that means in your original sample you are going to have 0.0025 moles of KOH, okay, because it's a 1-to-1 ratio. So those are the same. So where do we go from here? Well, if we know we have 0.0025 moles of KOH, and again, we're looking for molarity. Molarity, capital M, as we know, is moles over liters. Ah, darn it, we need that liter thing right there. Well, look at this. There's that 50 number. So we were able to put 0.05, because that's 50 milliliters in liters. Put the 1 on top. And then if you'll notice, your end unit is going to be mole divided by liter, and that's molarity. So that's cool. So if you calculate that out, if you do that correctly, you're going to come out with, oh, wait, I got to back us up here, folks. Put the wrong number down. Hopefully some of you caught that. That should not be 0.05. What should that be? 140, right? There you go. All right. Come on, Mr. Corner. Get with it, right? So 0.140 liters. That's better. All right. So if you calculate that out correctly, you're going to come out with 0.018 molar. And so that original potassium hydroxide solution that you had in that first Erlenmeyer flask that I drew, there was 140 mils in there. Well, we had that question mark molarity. What's that molarity? Boom, right there, 0.018. All right, so let's look at one other way to work this type of problem, or one other type of problem that may come up. A second type of problem is more commonly referred to as a neutralization problem. Same idea, just a little bit different terminology. So how many milliliters of a 0.715 molar HCl solution required to neutralize 1.25 grams of sodium carbonate? So HCl is your acid. You're going to add that to sodium carbonate. Neutralization or double replacement reaction, you're going to see NaCl plus H2CO3. Now you might say, well, Cornick, there's no water produced in this. However, we do have acids and bases. Acid, this is going to act as a base. We're going to have a conjugate acid and a conjugate base as well. On the other side, this is going to be your conjugate acid, and the chloride ion is going to actually act as your conjugate base. So this is kind of like an acid-base reaction in disguise. But don't worry, the stoichiometry doesn't change. It stays pretty much the same. All right, so what does that stoichiometry look like then? So we've got 1.25 grams of the sodium carbonate. Let me call that SC. Let me call that NaC. That'd be better. Just to shorten things up here, sodium carbonate, okay, over 1. The molar mass of that is going to be 106 grams per mole. Grams cancels out. At this point, I know how many moles of sodium carbonate I have, okay? So now we ask the question again, oh, if I know how many moles of sodium carbonate I have, I should be able to figure out how many moles of HCl I'll need to neutralize that. But one thing that you'll probably notice from this equation is it's not quite balanced yet. So you need a 2 there, right, and a 2 there. So at this step, we're actually going to have to use that mole ratio. For every 1 mole, rather, let's go back. Every 2 moles of HCl requires 1 mole of NaC. Okay, so that's going to give you moles of hydrochloric acid. And then to finish it out, because we're looking for milliliters, well, we have a molarity, so we should be able to say, okay, for every 1 liter, we'll add 0.715 moles of HCl, so those will go away. Okay, so that'll give you the total amount of milliliters. In this case, it'll be liters. That'll come out to, let's see, 0.033 liters, but if you do that quick transition, that's going to be 33 milliliters. All right, so that's a quick rendition of the stoichiometry that we will use when it comes to neutralization reactions.